This is Chapter 12, Module 4, the Action Potential. The learning objectives of this module are 1. Describe the events involved in the generation and propagation of an action potential, and 2. Describe the events that occur at the synapse. An action potential is a short-lasting event where the electrical charge of the membrane spikes quickly and then falls back to resting. Action potentials occur in many types of human cells that include the neurons, muscle cells, and the endocrine cells. In neurons, the action potentials play a central role in cell-to-cell communication. We've already reviewed in a previous module how the neuron has an established resting membrane potential. The resting membrane potential is the voltage inside the plasma membrane when it is -70 millivolts. The resting membrane potential can change when the permeability of the plasma membrane changes. This change in permeability occurs in response to a chemical or physical stimulus, and will cause additional ions to move into or out of the cell. The chemical or physical stimulus activates gated channels. An activated gated channel will open and will allow ions to pass through to the other side of the membrane. If the stimulus opens a sodium-gated channel, then sodium will diffuse down its concentration gradient and into the cell. When potassium-gated channels are activated, potassium will diffuse down its concentration gradient and out of the cell. Some gated channels open when stimulated by specific chemicals. These chemically gated channels are found on the neuron's cell body and the dendrites. Other gates open when they are activated by changes in the transmembrane potential. In other words, when the transmembrane potential at that segment of the membrane moves away from the -70 millivolts, it will activate gated channels in the adjacent segment of the membrane. These gates are found in the axons of the neuron and are called voltage-gated channels. When the resting cell membrane is exposed to a chemical stimulus, chemical-gated sodium channels open and sodium enters the cell. The sodium carries a positive charge and will cause the cytosol of the cell to become more positive. Since the resting cell's cytosol has an electrical charge of -70 millivolts, the charge will become more positive and move towards zero when sodium enters. The voltage will move to -69 millivolts, then -68 millivolts, then -67 millivolts, etc. Any shift in the transmembrane potential towards zero is called depolarization. As sodium is moving through the channel and into the cell, a local current is produced. The sodium ions inside the plasma membrane will spread to the adjacent plasma membrane, causing a local current at that location that is called a graded or local potential. The amount of depolarization and the change in the potential is proportional to the size of the stimulus. The stronger the stimulus, the greater the change in the transmembrane potential, and the larger the area affected. A change in the voltage, or in other words a change in the transmembrane potential, that is not strong enough to trigger an action potential will occur at the cell dendrites or cell bodies and will trigger specific cell functions in the cell body such as exocytosis of glandular secretions. The transmembrane potential is most changed at the site of the stimulation, and the effect on the membrane will decrease with distance from the original stimulus. The effect of the stimulus spreads passively due to local currents spreading the sodium ions to the adjacent plasma membrane. When the stimulus is removed, the transmembrane potential returns to normal as the sodium gates close. The excess sodium inside the cell is removed to the outside via the sodium-potassium pump. The excess positive charges clear out of the cell, and the transmembrane potential returns to -70 millivolts, which is the neuron's resting membrane potential. As the stimulus opens the chemically gated sodium channels found on the cell body or the dendrites of a neuron, sodium diffuses into the cell. This disturbance of the transmembrane potential moves the voltage from -70 millivolts to a more positive voltage, -69 millivolts to -68 millivolts to -67 millivolts, etc. If the stimulus is not big enough to raise the voltage to -60 millivolts, then the disturbance in the transmembrane potential will remain local, not traveling past the axon hillock, and will not be enough to trigger the voltage-gated channels found in the axon. The disturbance will get no further than the axon hillock. Any movement of the transmembrane potential toward a more positive number is called depolarization. So when the disturbance occurs, no matter how large or small, the plasma membrane becomes depolarized. If the stimulus is smaller and the membrane only depolarizes up to negative 61 millivolts, then the movement is called a graded potential. If the membrane depolarizes to negative 60 millivolts, this will trigger an action potential. When the initial stimulus causes a depolarization to negative 60 millivolts, the membrane potential reaches what is called the threshold. At this voltage, negative 60 millivolts, numerous local voltage-gated sodium channels will become activated and will open. The opening of these sodium channels allows a rapid influx of sodium ions into the cell, rapidly raising the charge inside the cell to more positive numbers. The charge rises from negative 60 millivolts to negative 50 millivolts to negative 40 millivolts to negative 30 millivolts to negative 20 millivolts to negative 10 millivolts to 0 to positive 10 to positive 20 to positive 30 millivolts very quickly. This is called rapid depolarization. When the voltage hits positive 30 millivolts, this triggers the sodium-gated channels to close. Since they don't all close at the same time, the voltage may continue to slightly rise above positive 30 millivolts. At the same time the sodium-gated channels close, which is positive 30 millivolts, potassium-gated channels open up. Potassium will diffuse out of the cell because of its concentration gradient. As it does so, the positive charges it carries will also leave the cell, and the interior of the cell will become more negative once again. Massive amounts of potassium leaving the cell through these voltage-gated channels cause the transmembrane potential to move to a more negative voltage. The voltage moves from positive 30 to positive 20 to positive 10 to 0, to negative 10 to negative 20 to negative 30 to negative 40 to negative 50 to negative 60 to negative 70. When the voltage hits negative 70 millivolts, the potassium channels close. But since not all the channels close at the same time, some potassium will continue to leak out, causing the voltage to drop below the negative 70 resting membrane potential to negative 80 millivolts. When the voltage drops below the resting membrane potential, it is called hyperpolarization. Hyperpolarization will continue until all the potassium-gated channels are closed and the voltage rises to negative 70 millivolts, which is the resting membrane potential. There is an all-or-none rule with action potentials that states that once a nerve fiber has reached threshold, an action potential will occur. In other words, if threshold is reached, an action potential will take place. If threshold is not reached, no action potential will take place. Also, when an action potential has begun, another action potential cannot take place at that segment of the membrane until the action potential is over. This is called the refractory period. An absolute refractory period is when the sodium channels are activated and no matter how large a second stimulus is, another action potential would not be possible. A relative refractory period is when the transmembrane potential is close to normal and a very large stimulus could initiate another action potential. The voltage-gated channels are found on the axon of the neuron from the initial segment of the axon to the end of the axon at the synaptic terminal. If the graded potential at the axon hillock is strong enough for the membrane potential to reach threshold, an action potential will occur at the initial segment of the axon as the sodium-gated channels open. The action potential is a very rapid depolarization of the membrane that is strong enough to trigger the adjacent portion of the membrane on the cell axon to depolarize it, which in turn causes the next adjacent portion of the membrane on the axon to depolarize. Each action potential that is generated will trigger another action potential on the axon just adjacent and just distal to it. Each action potential produced will occur on a segment closer to the end of the axon that is called the synaptic terminal. Each action potential triggers another action potential closer to the synaptic terminal. So the first action potential created occurs at the initial segment of the axon, and the last action potential created occurs at the synaptic terminal. All of the action potentials that are generated from one initial action potential in the initial segment of the axon are collectively known as a nerve impulse. The final action potential that occurs at the synaptic terminal will be able to stimulate the release of neurotransmitters from the synaptic terminal and into the synaptic cleft. Neurotransmitters are chemical messengers that can stimulate another neuron or cell to become depolarized. The neuron that is releasing the neurotransmitter is called the presynaptic cell, and the cell that the neurotransmitter binds to is called the postsynaptic cell. The events that occur between the presynaptic cell and the postsynaptic cell is called a synapse. The neurotransmitter has the ability to either excite the postsynaptic cell or it will inhibit the postsynaptic cell. Acetylcholine is a neurotransmitter commonly used between two neurons and also between a neuron and a muscle cell, or between a neuron and a gland. When acetylcholine is the neurotransmitter that is released, the synapse is called a cholinergic synapse. Specific events occur at a cholinergic synapse. First, an action potential arrives at the synaptic terminal. This action potential depolarizes the synaptic terminal, opening calcium-gated channels and allowing calcium ions to enter the synaptic terminal. This influx of calcium into the synaptic terminal causes vesicles filled with acetylcholine to undergo exocytosis, expelling the acetylcholine into the synaptic cleft. ACH diffuses across the synaptic cleft, binding to ACH receptors on the postsynaptic membrane. The binding of ACH on the receptors causes sodium-gated channels to open on the postsynaptic membrane, causing a massive influx of sodium ions into the postsynaptic cell. This influx of sodium ions depolarizes the postsynaptic membrane, resulting in the generation of an action potential on the postsynaptic cell. Finally, when the nerve impulse ends in the presynaptic cell, the excess acetylcholine in the synaptic cleft will be removed by an enzyme called acetylcholinesterase. Acetylcholine is not the only transmitter used in the human body. Other important neurotransmitters include norepinephrine, dopamine, serotonin, and gamma-aminobutyric acid. Action potentials generated at the axon hillock will move along the entire length of the axon. This movement of the action potentials is called propagation. There are two methods of propagating action potentials: continuous propagation and saltatory propagation. Continuous propagation occurs in axons that are unmyelinated, while saltatory propagation occurs in axons that are myelinated. In continuous propagation, where the axon is unmyelinated, an action potential begins at the segment of the axon membrane in the initial segment of the axon. Once the membrane depolarizes to positive 30 millivolts, the positive charges move to the adjacent membrane through a local current in the axoplasm. The positive charges at this adjacent membrane depolarizes this segment of the membrane to reach threshold, causing this segment to develop an action potential. The positive charges from this depolarization move to the next segment on the membrane, and that segment depolarizes enough to develop an action potential. The local current continues to carry the positive charges to each adjacent segment of the membrane, creating action potentials that occur closer and closer to the synaptic terminal. These action potentials only move in one direction, toward the synaptic terminal. In saltatory propagation, where the axon is myelinated, the action potentials will be created faster and use less energy than in an unmyelinated axon. Myelin insulates the axon and prevents continuous myelination. The myelin is produced by the nucleus of the Schwann cell and creates internodes of myelin along the axon. In between the internodes are bare areas of axon called the nodes, or the nodes of Ranvier. Because of the myelin covering, sodium is unable to cross the membrane wherever there is an internode. The internode acts as a barrier. The only place sodium can influx into the axon is at the nodes, where there is no myelin. In this manner, the action potentials can skip or jump large areas of axon. Instead of an action potential being created at the next segment, as in the unmyelinated axon, action potentials in a myelinated axon will be created several segments down the axon, because depolarization can only occur where the axon is exposed to the extracellular fluid and sodium can enter through the open gated channels. This allows the movement of action potentials, or propagation of action potentials, to move much faster down the axon toward the synaptic terminal. Think of an elevator that you are in that is on the 23rd floor of a building. If you had to stop at every level to allow other passengers in as you make your way to the ground floor, it would take you much longer than if you only stopped at a few floors. The myelinated axon allows a faster movement toward the synaptic terminal. just as the case of an elevator that only had to stop at a few floors on the way down to the ground floor. This ends Chapter 12, Module 4, the action potential.